Hello, dear students. This is Professor Pino, and today we are going to study Chapter 10 in Week 3. Is the second lecture about energy. Well, first of all, what is energy? Energy is the ability to do work or produce heat. The law of conservation of energy says energy can be converted from one form to another, but can be neither created nor destroyed. Then the total energy content of the universe is constant. You cannot create or destroy energy. Only you can go from one form of energy to another type. For example, you can use the energy in your food to produce energy that you can use for different activities in your daily in your real life. Energy can be divided in two main parts, potential and kinetic. The potential energy depends on the position or composition. If it is a chemical, depends on the composition to produce energy. But if it is an object, depends on the position, how high it is. The higher is the object, the more energy can produce. Kinetic energy is related to the motion and depends on the mass and the velocity of the mobile. As you can see here, A contains more potential energy than B because it's at a higher altitude. Well, we can speak about heat. Heat is a type of energy and involves the transfer of energy, in this case heat, between two objects due to a temperature difference. Work is the force acting over a distance. And the energy is a state function. Why a state function? Because it's a property that does not depend in any way on a system's past or future. Depends on the system state, present state, and changes independently on its pathway. Work and heat are not state functions because they depend on the pathway. The nature of the temperature, well, the distance traveled from one location to another is not a state function because depends on the route taken. The change in elevation is a state function. Change in elevation is always the same, does not depend on the route taken. Then remember that when we are in present of a state function, when doesn't depend on the way taken, only depends on the initial and final state of the energy or of the object. Temperature measure of a random motion of the components on a substance. For example, here in hot water, the particles have more energy than in cold water. if you put hot water besides cold water, there will be a flow of energy from the hot water to the cold water until you get an equilibrium. In this case, 50 Celsius degree in both sides. What is a system? It's a part of the universe on which we wish to focus our attention. The surroundings include everything else in the universe. The systems can be exothermic or endothermic. It depends on the change of the energy. For example, if the reactants in a chemical reactions has more potential energy than the products, then some energy is released to the surrounding as heat. And this is an exothermic reaction because releases energy to the surrounding. Then, endothermic process. Heat flows is into a system, absorbs energy from the surroundings. Exothermic process. Energy flows out of the system. Energy gained by the surrounding must be equal to the energy that is lost by the system. Lexi, is freezing water an endothermic or exothermic process? Explain. Well, in order to freeze energy, you have to release energy. Then this is an exothermic process. Classify the following process into exothermic or endothermic. Well, your hands get cold when you touch ice. In this case, it's exo because your hands are releasing energy. The ice gets warmer when you touch it. It's an endothermic reaction because the ice gets energy from your hands. Water boils in a kettle being heated on a stove. Well, in this case, it's an endothermic process because water is gaining energy from the stove. Water vapor condenses on a cold pipe. This is exothermic because water, in order to go from the into a cold system, has to release energy. Endo is also an ice cream with melts because it's absorbing energy in order to go to from the solid state to the liquid state. Well, we can say that, for example, for each of the following, define a system and its surroundings. Methane is burning in a Bunsen burner in a laboratory. Well, the system here is what is happening in the Bunsen burner. This is the energy, and the space around the Bunsen burner is the surrounding. Well, try this one. After swimming, water drops on your skin. Water drops on your skin, evaporate. Tell me, what is the system and what is the surrounding? Here you have another example. Try to go over these. Remember that every week you have a lecture. It's a PowerPoint like this that you can find in content. If you open content, you will have every week a lecture. Well, thermodynamics. Let's see. What is internal energy? Internal energy, or E, of a system is the sum of the kinetic and the potential energy of all particles in the system. The change in the internal energy of a system is represented by the sum of the heat plus the work done or by the system or done over the system. If the process is endothermic, Q is positive. If the process is endothermic, Q is negative. This is a way to represent it. Look at this. Here, the energy goes from the system to the surroundings. So the internal energy is negative. The opposite, if energy goes from the surroundings into the system is gaining energy, then the internal energy is positive. The work is negative, then the system does the work on the surroundings. But if the work is positive, then the surroundings do work on the system. These concepts are very, very important. You can write them in your notebooks, and you can use these notes during the exams and also during your homework. Well, here you have another exercise. But let me go into the energy units. Calorie is the amount of energy or heat required to raise the temperature of 1 gram of water by 1 Celsius degree. This is a concept of what is a calorie. And a joule is equal to 4.184. Oh, sorry, 1 calorie is equal to 4.184 joules. Don't forget this because you're going to use this in problems. For example, convert 60.1 calories into joules. You say 1 calorie is 4.184 joules. And you use this as a conversion factor. Then you put calorie down in order to cancel calorie with calorie. And then you multiply and divide and you get the answer in joules. Remember, as the given number has 3 significant figures, you have to report 3 significant figures in your answer. Every time you do a conversion, you have to follow this rule. Well, energy, in this case heat, required to change the temperature of a substance depends on what? In the amount of substance. Then it is the number of grams. The temperature change in the number of degrees, Celsius, Kelvin, or whatever. Identity of a substance, a specific heat capacity. What is a specific heat capacity? Is the energy required to change the temperature of 1 gram of a substance in 1 Celsius degree. Every substance has a specific heat capacity. Is a physical characteristic of every substance. Here you can see in this table the specific heat capacity of different substances expressed in joule per gram per Celsius degree. Look at this. Water liquid has the higher specific heat capacity. What does it mean? That in order to change the temperature in 1 Celsius degree, water can absorb a lot of energy, more than any other substance that you know. That's why the changes of the temperature in the oceans is very low and very slowly, because water can absorb a lot of energy. And that's why the temperature in the surface of air is cannot change so much, because water in the ocean that represents 70% of our planet's surface can absorb most of the energy that comes from the sun. Look at this. The energy, in this case heat, that is represented by Q is equal to S, that is the specific heat capacity, M, that is the mass expressed in grams, and delta T, that is the change of temperature that is expressed in Celsius. Always delta T is the final minus the initial temperature. For example, calculate the amount of heat energy in joules needed to raise the temperature of 6.25 grams of water from 21.0 Celsius to 39.0 Celsius. Then you go to the formula and you say the specific heat of water is this. This is the mass of the water, and then you subtract the final temperature minus the initial temperature, and you get this in joules, the amount of heat needed to change the temperature from 20 to 39 Celsius degree of this amount of substance of water. Well, here you have other calculation. You can stop the video at any time and you can see this problem. The answer here is 19 grams. A problem like this can be in your first exam. So pay close attention to this question. Here you have another example, another, and another example here. Okay. Well. What is the change in enthalpy? You can say that the enthalpy of a chemical reaction is the amount of heat at constant pressure. Then it is the delta H P. This is heat. Here you have a reaction. Sulfur solid combines to or with oxygen gas and produces a sulfur dioxide, that is a gas. This is the enthalpy of to form 1 mole of this substance. Then you have to to calculate the quantity of heat released when 2.10 grams of sulfur is burned in oxygen at constant temperature. So, you know that one mole is formed, when 1 mole of this substance is formed, this amount of energy is released. It's released because it's negative. And we have 2.10 grams of sulfur. So what you have to do? You have to write the reaction, and 2.10 grams of sulfur is, if 1 mole of sulfur is 32.0 grams of sulfur, you can get this number in the periodic table. Is the atomic mass of sulfur. One mole is this mass of sulfur. Then you can calculate using this equation the moles of sulfur. And you know that 1 mole of sulfur produces 1 mole of sulfur dioxide. And 1 mole of sulfur dioxide releases this amount of energy. Then you can do this operation, and the answer will be that during this reaction in front of this amount of sulfur, you can release 19.4 kilojoules. Here you have another example. You can go to your PowerPoint in the in the content of week number 3, and you can see how to do this reaction. Okay, until here is the part of chapter 10 that goes to this week.